Hey there, folks. This is Mr. Young, and I am going to give you a little bit of an introduction to different types of nuclear radiation. So here's where you need to be. You need to be on page 15, in your unit pack. All right, so nuclear radiation. This is where we start to mix together mass and energy a little bit. So nuclear radiation can mean particles, or it can mean energy that are emitted from a radioactive or a decaying nucleus. A nucleus that is decaying is radioactive because while it is decaying, it is emitting particles and or energy. That's what nuclear radiation is. Particles and or energy emitted from a decaying nucleus, a radioactive nucleus. Why does this happen? Well, a nucleus that is unstable can emit particles or energy to become more stable. So if you've got something that's radioactive, it is unstable and it will emit nuclear radiation. That means particles and or energy to become more stable. What do we mean by unstable? Well, any nuclei that has a neutron to proton ratio, that would be like the number of neutrons divided by the number of protons. If that ratio is too high or too low, a stable ratio of neutrons to protons would be between 1.1 and 1.5. Everything else is unstable. Basically, atoms are stable if the number of neutrons and protons are pretty close to each other, or if you just have a few more neutrons than protons. But if you have a lot of extra neutrons, that's unstable. Or if you have a lot of extra protons, that's unstable. Here is a diagram that you have on page 17. This diagram is showing all the stable isotopes. Okay, all these black dots are all the stable isotopes. A neutron to proton ratio of 1 to 1 is right here. Neutron to proton ratio of 1.5 to 1 is right here. So all the stable isotopes, they exist within here. At first, things are really stable when they have the exact same number of neutrons and protons. As things get bigger, they can handle having a few more neutrons. But if we get too many neutrons or too many protons, then we're not stable. So this is the stable range. Up here, too many neutrons compared to the protons would be unstable. Down here, more protons than neutrons would also be unstable. Okay. So types of radiation that are emitted by atoms that are unstable. You're going to get some help filling this out from Table O. So take a moment to open up Table O while we fill out this chart. Okay. All right, let's see here. And one thing I want to let you know about notation is that previously we've written a helium atom like this. We've got helium, it has a mass number of 4, and it has an atomic number of 2. Okay, now we're going to start expanding what information these numbers here give us. This is the mass number, the protons plus neutrons. And so far, this has been the atomic number, the number of protons, okay? But here's how we're going to think of it now. This number up here is going to tell us the mass of any type of particle, okay? And that's going to include these different types of radiation. And this down here tells us the charge. If it is a positive 2, like 2 protons, well, then it's a +2 charge. And we're going to start seeing negative numbers down here for negative particles like electrons and some other things. Okay, so this number up here means the mass, this number down here means the charge. And so far that has meant just protons, but now there can be negative charges down here too. Okay, so if you look at Table O, there's a special symbol for alpha particles. Okay, alpha particles are drawn like this. It is a Greek letter alpha. Okay, it looks kind of like a fat sideways fish. Okay, as far as notation, alpha particles are actually a helium nucleus without any of the electrons. So it's got 2 neutrons and 2 protons, so it has a mass of 4, okay? And it's got 2 protons, so it has a charge of 2, and that would be a +2, okay? You might also see this written, the alpha symbol, and a 4 and a 2. What's the mass? The mass is 4 because it has 2 protons and 2 neutrons. What's the charge? The charge is +2. Why? Whoops. sorry about that, plus 2. Why charge of plus 2? Because it has 2 protons. Okay. These particles, in terms of their energy and their penetrating party, they're kind of big and clumsy. They have a low energy, low penetrating power. That means what types of materials can alpha radiation travel through. So alpha particles, here's the symbol, here's the notation. Whoops, that's an He. They are helium nuclei. Mass of 4, charge of 2. They're big and clumsy, low energy, low penetrating power. Beta particles, they have a special symbol that you can see in table O. It is sort of like a fancy bee with the tail off of it. Okay, it's got a negative. The funny thing about a beta particle is it's just a fancy name for an electron. So the notation for this will be E with a 0 up here because electrons have no mass, and a -1 down here because electrons have a charge of -1. You also might see this written like this, a B for beta with a 0 and a -1 down here. What's the mass of an electron? 0. What the heck? Let's write this here. Beta particle is also an electron. Here's the way we've been writing electrons up till now. The charge of an electron, it's -1. It's an electron. Okay. Beta particles are actually reasonably energetic, and they have pretty good penetrating power. They can go through lots of materials. So we'll say they have medium energy, and they have medium penetrating power for blasting through materials. Okay, next up, a weird particle that you might think sounds like something from science fiction, but it's a real particle. It is a positron. A positron is basically like the opposite of an electron. So we represent it with a B for beta plus, okay? And so the symbol for this could be an E0 with a +1 down here. It's like an anti-electron, okay? And you also might see its symbol written this way, and these are both in table O. Okay, what's its mass? Just like an electron, it has a mass of 0, but it's an anti-electron. It's a positron. It has a charge of +1. Just like an electron, it has medium energy and medium penetrating power for blasting through materials. Okay, finally, the last important particle is actually a form of energy. This is gamma particles, or can also be called gamma radiation. That is more correct, gamma radiation. Okay, and the special symbol for this is a Greek letter gamma. Looks like a fish standing on its head. Gamma radiation, it has no mass because it's a form of radiation, and it has no charge, so 0 and 0. Has no mass, mass of 0, has no charge, charge of 0. Gamma radiation is pretty bad stuff. It's got high energy, and it can penetrate through lots of materials. This is very powerful kind of radiation, okay? All right, last up, just going to create emoji for these to help you remember them. Okay, a helium nuclei is an alpha particle. So we're going to draw this as just 2 positive protons and 2 neutral neutrons stuck together. This is what's in the nuclei of a helium atom. There are no electrons. 2 neutrons, 2 protons, and ta-da, here's what it is. It's just a helium nucleus. Okay, this one, it's smaller. It's just an electron. There we go. And what is it saying? Oh, I have almost no mass, or basically no mass. Okay, that's a beta particle or an electron. We've got a positron, which is like an anti-electron, and there we go. I'm like an anti-electron. And finally, our last emoji, gamma radiation, will represent with some waves because radiation is a form of energy, and it is in waves. Okay, so gamma particles are just energy, right? Last up, you already know about neutrons and protons. The symbol for a neutron in this type of new notation is mass of 1, charge of 0. Okay, they are neutral, 1 atomic mass unit, or 1 U for unit. Protons, we could write them this way. They're like hydrogen nuclei, or we could also write them this way, a proton with a mass of 1 and a charge of 1, meaning +1. They are